So, looked at the notes yesterday. There's going to be a decent amount of notes, at least on this first page here as we go through and look at stuff. But randomization and statistics in data collection, we use, I'm going to write in a different color than I normally do. We are going to use random sampling to avoid bias. And bias specifically is when the statistic, from your sample over or underestimates your population parameter and there's going to be a whole pretty much chapter about bias. I can't remember if it's chapter 13 or if it waits till chapter 14, but I'm pretty sure it's in this unit. So it's got to be sometime before chapter 13. But when we're collecting data, we want it to be random, and there's going to be a whole, deal about that also. In experiments, we use a random assignment of subjects to treatments. And again, we'll have a whole pretty much thing about that, about we're obviously talking about randomness in this chapter, but about randomly assigning groups of people and breaking things down to avoid bias and how to go about blocking and all of those things. But essentially randomly, if we have, a group of 20 people and we're going to have 4 groups of 5, then I'm going to put everybody's name in a hat and then draw them out randomly to make sure that I have random stuff and I'm not causing a bias essentially to come in by me being well, you 5 all have blonde hair, so I'm going to throw you in this group. We want things to be random, and if it so happens that ends up being how it is, that's fine, but at least we did our best to keep stuff random so that we can have more accurate information. Randomization allows us to equalize the effects of unknown and uncontrollable sources of variation among treatment groups. So essentially, if we were gonna analyze for, say, diet, right, and we're gonna put people on, test different people for different diets, I don't want to put everyone that, if all I'm looking at is strictly a diet and nothing else, I don't want to be well, I know that these 5 people work out every day, so I'm going to put them all in one group. That's not going to be helpful. Again, if it randomly happens that is what occurs, that's fine, but I don't want to intentionally have that, and so that's why randomization can help with that process. All right, I'm going to write down 4 numbers. Josh, I need you to do this too for me. I want you to randomly select a number, but don't say it out loud, just write it on your paper. You don't have to actually write it unless you just want to. I need your thing. All right. Virginia, what number did you pick?
4.
Chris, what number did you pick?
4.
Josh, what number did you pick?
2.
And I also picked 4. I just didn't obviously write it because So, that being said, 75% of us picked the number 4. 25% picked 2. And 0% chose 1 or 3. So essentially that's just showing you, like, you know, obviously we all had our own thing. One of you didn't dictate what the other one was going to say. It was all random. I chose 4 because that's like well, I'm not going to say that's my favorite number. 14 is probably my favorite number, but 4 is in 14, so, you know, whatever.
So was 1, though.
Yeah, but 4 was, like, my number when I started playing sports, but then, like, as I went up, like, 4 wasn't an option anymore, but 14 was, so, like, I took 14. I don't know. I don't really care. Like, everybody's like, I have a favorite number. I'm like, I mean, I have one I would choose if it's, like, an option, but, you know, whatever. Okay, so, if I were to select a student at random, what does that mean to you? Like, if I had, like, think back to elementary school, like, or I think my mom may have done this if you had my mom, I don't know, but there was, like cup, and there would be, like, popsicle sticks in there, and, like, every student's name was in there, like, one time, or, like, maybe it was a number, and it was associated, like, alphabetically with, like, where you were in the class or whatever. So, like, I was number 2 in my class, so, like,
so if you picked...
if, like, the number 2 was selected, then I knew that she was calling on me. So, if I were to do something like that where I select a student at random, or let's say I turn around and y'all mix up your seats and I'm, like, right there, right? So, like, I don't know where you are.
Would it be there's, like...
There's no bias. What else?
There's a 33% chance of being picked.
Yeah. So it's everyone has an equal chance of being picked, right?
Okay.
Like, that's what I'm going for. So... you don't know who's getting chosen. I don't even know who's getting chosen because y'all have mixed yourselves up, or I've been like, all right, you know, Chris is blue, Josh is yellow, and Virginia's pink, and then I randomly pick one. I don't know where they are in here, and I grab one, and, well, this one's gray, but bad example, but you know what I mean, right? Yeah. Like, if there were more people, then obviously I could be like, okay, well, everyone's a Sharpie, and whatever one I pick, that's who it is, or whatever. Everyone has an equal chance of being chosen, and we don't know who's going to be chosen. So, we don't know who will be chosen. And everyone has an equal chance to be picked. All right, so what can go wrong? So don't overstate cases, meaning essentially a simulation shows what might happen. Where might is the key word. Not what will happen. So we also want to model potential outcomes accurately. So basically, there's going to be 2 things under here. Don't imply, don't imply outcomes are equally likely. unless they are. So, like, in here, I have, with my Sharpies, I only have 3 pink markers. But I have 4 yellow markers, and I have 5 blue markers. So I don't want to say that all of you have an equal chance of being chosen if I've assigned a color to each of you, right? If there's a different amount in here. So I would say, well, Virginia has, however many I think there's 12. Well, she has a 3 out of 12 chance of being chosen, but you have a 5 out of 12 chance of being chosen, and he has a 4 out of 12 chance of being chosen. Like, everybody has a different amount. So don't say everyone has an equal amount unless we know that that's essentially true. And then don't lump together outcomes, model all potential outcomes. And then run enough trials. We talked about this yesterday. Don't make judgments. On a few number of trials. Now, there are going to be times where I tell you just to run 3 or 5 for the sake of time. But if we're doing something by hand, we want to run 20 trials. And typically when I'm saying 20 trials by hand, what I'm meaning is use your calculator to run that, because I'm trying to save you time from you having to look at a random number table and look at each individual thing, because that just can be a pain. If we're using a computer that essentially we can hit a button and it can run all the trials essentially back to back to each other, I want to run about 100 to be sure. Where it's going to analyze for you, and it's going to be like, all right, I ran 100 trials, and here's the results of these trials. Like, you can still see the output of what each trial gave you, but the ultimate thing at the end is it's already analyzed it for you. Whereas, by hand or using your calculator to produce numbers, you're still having to calculate these things yourself. Okay. Y'all have all this. Okay. All right, so in each of these, I want to explain why it fails to model the situation properly. So the first one is to use random numbers 2 through 12 to represent the sum of the faces when 2 dice are rolled. Okay, so I wish I had them here, but I don't have any with me. So if I rolled 2 dice, right, the minimum sum of a fair 6-sided dice would be 2. The maximum if I roll a 6 on both is 12, right? So to roll a 3, I can have 1 dice be 1 and 1 be 2, or vice versa. But what about rolling a 4? Just a sum of 4. What different ways can that happen?
2 and 2, and 1 and 3.
Yeah, 2 and 2, or 1 and 3, and obviously vice versa on those. How about 7?
5 and 2, 3 and 4, and 6 and 1.
Yeah. So there's a lot more ways that can happen, right? And I think that's the one that has the most ways that it can happen. maybe not. 8 might be the most. I don't remember. Anyways, but you get the point that all outcomes aren't equally likely, right? Or like the total like amount. So not all outcomes are equally likely. For example, like we just said, a sum of 7 is more likely than a sum of 2. So if I actually wanted to run this like as a correct simulation, there is, let me find it and how to get there. It's been a while. Okay, so on your calculator, let's just give you a little intro. Obviously, it's not asking us to do anything other than explain what the problem is. But if you hit the math button and you arrow over to probability, so that's as far over as it goes, and then you go down, you're going to see this RANDINT, that's random integer. Then what we put in here is the first number that's an option and the last number that's an option. So essentially on a dice, I can get 1 through 6. So 1, there's a little comma button as soon as I find where it is. Where's the comma?
I think it might be somewhere below like sign. Maybe.
That's where I was looking. Oh, I see it. Thanks. I was looking at a second button, not an actual button. So 1, 6, comma, and then I'm looking at 2 things at a time. So 2, and I hit enter. So the first time I roll a 2 and a 6. If I hit it again, the next time a 6 and a 2. So both of those have given me a sum of 8 so far. 6 and 2 again. 3 and 3. So now I have a sum of 6. And you can keep doing that, and now I have a sum of 12, which can only happen one way, right? So essentially, that's just a way that you can actually run your trials, is using random integers. There's another way that I'll show you when we actually get running trials and stuff. But I'm just going to go ahead and note how you would do this on your calculator so that you know. But we would do, you hit math, PRB for probability, and then random integer. Then as far as what goes in, so for this one I would do random integer 1, 6, 2, which says the numbers 1 through 6, and there are 2 of them. So this next one's kind of interesting. It says to use a random integer from 0 through 5 to represent the number of boys in a family of 5 children. What do you think about this one?
Maybe there's an equal chance of getting like a boy or a girl. So I don't know if it's like, so it would.
It's like the outcomes are equally likely or no?
So we're looking at the number of boys in a family.
Like
So the outcome is equally likely to get a girl versus a boy for each child. But as far as getting a family of all boys or all girls, that's way more difficult, right, than getting 3 and 2. Right? So, like, because it's just you and your sister. But you, Chris, don't you have like 3 sisters? So there's like 3 girls, 1 boy, right? So the outcome, and obviously family to family is always going to be different. But hypothetically speaking, it's going to be way easier to get a mix of boys and girls versus getting all boys or all girls, right? So not all outcomes are equally likely. All boys is less likely than 3 boys, 2 girls. Or really any other combination. Once we get into more of actual probability, we'd be able to see why, but so the way that they have quote unquote suggested to do it in this particular problem is to basically say that we're using random numbers from 0 through 5, and that's going to tell us how many boys are in that family of 5. Okay, so essentially if I run the numbers, 0 through 5 one at a time, and I do it for each family, and I do it 20 times, I'm going to be able to see how many boys they got in each case. When I've done it that way before, I've never had a situation where they had 0. I have had quite a lot where there were 2 boys or 3 boys, and I've only ever had one that they had 4 boys and one that they had 5 boys. So it's just very interesting, like when I've run the, random numbers, how it comes out. But in my opinion, a better way to model this would be to say that boys are 1 and girls are 0. And to use my random number generator here and let it produce and tell me how many of each I'm going to have. So I'm going to have random integer, 0 and 1. Oops. And I need 5 at a time. So then the number of boys. So, and you can do this if you want for your own individual, or we can just do it as a collective group. But I'm going to type in my random integer. I'm going to do 0, 1, 5. And when I do that, it's going to produce 5 numbers for me. So boys are 1, that's all I care about. So 1, 2, 3. So I had 3 boys the first time. Run it again. I only got 1 boy. I got 1 again. I got 3 that time. I got 2 that time. And I'm going to run 20, so I've a fourth of the way there. I got 1. I got 2. I got 4. I got 2. I got 3. I got 1. 4. Ooh, I got one that was none. I got 3. Oh, I got all 5. I got 3. I got 3. 2. 3. 4. All right, so now I'm going to do an analysis of how many times I got each. So 0, 1, 2, 3, 4, and 5. So 0, I only had that one time. 1, I had that 1, 2, 3, 4 times. 2, I had that 1, 2, 3, 4 times. 3 was 1, 2, 3, 4, 5, 6, 7 times. 4, I had 1, 2, 3 times. And 5, I had 1 time. So basically, I would take this number and divide it by 20. So, and that'll give me the percent for how likely it is to occur. So essentially, there's a 5% chance I get no boys. There's a 20% chance of getting just 1 or 2 because that was the same number.
Wait, how are we finding the percents again?
I'm just taking this number and dividing it by 20 because that's how many trials I ran. 7 out of 20. So there's a 35% chance of 3 boys. 3 out of 20. There's a 15% chance that I get 4. And then all 5 is still just 5%, just like getting no boys. So essentially, according to this, I have an equal chance of getting no boys or getting all boys. And then my highest would be to get 3 boys, essentially, is what that says. All right, so then this last one, simulate a baseball player's performance at bat by letting 0 be an out, 1 be a single, 2 be a double, 3 be a triple, and 4 be a home run. So, I don't know how much y'all know about baseball, but what would the problem with this be potentially?
There can be different things that happen that like aren't the player's fault. Like if someone else like I don't know, like someone else's performance can cause it to be an out or something.
That's a possibility. So, statistically speaking, a triple is one of the hardest things to get in baseball because typically it's like you either get a home run or you're getting like a single or a double. It's very rare that somebody gets a triple. So, essentially, still all outcomes aren't equally likely. And also, at the level we're talking about, let's say we're talking about MLB, it's way more likely that they get out than that they get on base most of the time. If they get on base 3 out of 10 times, that's considered really good. So, not all outcomes are equally likely. And so essentially they would have to tell us the probability of each outcome before we could run a simulation. So we would essentially need to say something like, you know, they get a single 5 out of every 10 at bats or something like that. They get a double 2 out of every 10 at bats. They get a triple 1 out of every 10, or, you know, something like that for us to be able to actually run this effectively to do that. So, anyways, that's that. The next example is pretty long, and I don't want us to stop in the middle, so we'll just go ahead and stop there and just pick up on number 4 tomorrow. And we'll just see how far we get based on that.